This talk is a continuation of the lecture of Jan Fyodorov this morning. So I'll try to show you how to apply supersymmetric approach and in all details in the case of the density of states for a Gaussian unitary ensemble. That's the easiest possible example. Now, before I will take 5 minutes to just summarize the general context of the lectures you have seen this week. So, well, random matrix theory is the study of large matrices whose elements are random variables. Now, you have seen random Schrödinger, but the number of applications of random matrices is huge. Now, just to give a list in physics, well, it was introduced to study the energy levels of complex many-body systems. So you have to study, for instance, the energy levels of a big nucleus or a very complicated molecule. And later on, it was very useful in mesoscopic physics. And this means disordered conductors. And it's in this context that random Schrödinger operator appears. And you have heard a lot about random Schrödinger, and you will still hear a lot about random Schrödinger. And also quantum chaos. Well, actually, there are other fields in physics where random matrices appear. For instance, 2D quantum gravity, conformal field theory, QCD, and I'm sure there are others. So you have the choice. Well, actually, also for mathematicians, also in mathematics, there are applications for random matrix theory, who seem to have nothing to do with what I said. I'm sorry. So first thing, the zeros of Riemann zeta function. For mysterious reasons, the zeros of the Riemann zeta functions seem to have the same distribution of the energy levels of a certain set of random matrices. There is no explanation for that, but that's how it is. And then, well, the study of random permutations, random tiling, growth processes, and so on and so on. So this is just to say that the applications in mesoscopic physics, and so random Schrödinger, is just a part of a huge number of applications for random matrices. So what is the problem? Now we have a matrix which I pretend is self-adjoint to simplify n by n, and a certain probability measure. I. Where dH is the Lebesgue measure. Okay, now, what are the possible properties of the probability P of H? Well, there are two main cases. First thing, since we are working with self-adjoint matrices, you can ask if P is invariant under unitary rotations. That means P of U H U star is equal to P of H for all U star U is 1. Physically, this means that the particular reference system doesn't matter. The system looks the same however you look at it. Second property, you could have statistical invariance, independence. Of the matrix elements. That means that you know as little as possible about your physical system. Now you know that if x1, x2 are independent, then the probability, the joint probability, has to be a product of a function of x1 and a function of x2. Could be two different functions, but the probability is a product. So in the case of a matrix, this means that P of H has to be proportional up to constant to a product I smaller than J of in a self-adjoint matrix, you have what are the independent pieces? Well, on the diagonal, you have real elements, yes? Sorry, just to call it different, I could call it a function. What I mean is that this density is a product of functions. And I actually could have different functions for each ij element. And I could have a different function for the real part and the imaginary part, in principle. Okay, now, I would like to say, well, can I have both properties together? That would be very nice. Well, actually, this is possible only in one case, when you have a Gaussian distribution. And now I don't know how to make that. That means that P of H is equal up to a normalization factor to e to the minus n over 2 trace of H squared. Well, here I can choose a different constant, and I could add here a linear piece and a constant. But I can always re-put them back in this expression by some translation. So I just consider this. Now, why is this? Why 1 and 2 are valid? Well, for 1, you see that H appears in a trace. So trace of U H U star square is equal to trace of H square. And why do I have statistical independence? Well, because E minus n over 2 trace of H square, this is just sum over I and j, Hij, Hji. But that is Hij complex conjugate, because it's self-adjoint. So here I have the absolute value of Hij square. So I can rewrite this as sum over I smaller than j of n, real part of Hij square plus imaginary part of Hij square, E minus n over 2 sum over j. So indeed I have a product. In general, I cannot have 1 and 2 together. If I want to use a probability distribution that is not Gaussian, I have to give up either the invariance, either the statistical independence. Okay, now, Oops. Now, in the same way, we have these two situations. According to the different cases, we have different techniques to study the problem. First case, P is invariant. Well, then we can diagonalize H. H is U, and this is diagonal. And since the probability is independent, P of H is actually P of just the eigenvalues.
Invariant.
Sorry, yes, as P is invariant. So in the particular case, if you have trace of H square, this becomes sum J from 1 to n of lambda J square. So this means that we can actually integrate out the unitary rotations and get an effective explicit expression for the probability of the eigenvalues. I will call it little p. I mean, it's another expression, lambda 1, lambda n. And in the case of GUE, this is proportional to, well, some constant times E minus n over 2 sum over j lambda j square. And the moment we decided to use as variables the eigenvalues and the unitary transformations, we have a Jacobian because we are doing a change of variables. And the Jacobian is the van der Monde determinant square. Now, once we have this, well, then there is a very powerful technique which is called orthogonal polynomials and the Riemann-Hilbert approach. And there is a big mathematical community working on this kind of problem. I won't talk about orthogonal polynomials. Now, in mathematics, most mathematicians work on this kind of problem. So the problem when the probability distribution is invariant under unitary rotations. And then you can actually end up with an explicit expression for the joint probability of the eigenvalues. Okay, what is the other situation? Well, the probability is not invariant. And now I lost. Where can I? And please, if you don't understand something, just stop me. This is supposed to be a summary and a simple example. Well, it turns out that mesoscopic physics problems fall all into this category. So the situation when the probability distribution is not invariant. Otherwise, life would be much easier. Well, in this case, so this is middle. Well, we cannot use the classical techniques. There is no way to get an explicit expression for the joint probability distribution. So we have to work with P of H. And the technique which is more widely used is supersymmetry. And indeed, you can get a lot of results. And that's the reason why you are struggling to understand something about supersymmetry. Okay, so.
Yeah, but you still have to assume something about the distribution of H. So what
you
do
mean?
assume?
Well, I mean, the computations are easier if you use a distribution which is, I mean, they are very easy when you have a Gaussian distribution or something similar. But you can do stuff also when it's smooth, a smooth distribution. And people do a lot of stuff with supersymmetry. Even when, it's very different to say, I mean, to get some results and then to prove them rigorously.
So it depends on which method you understand. Jan had two methods. If you only know the Haber-Satonovich transformation method, then you can only do Gaussian distributions. However, if you learn this bosonization, then you can actually attack more general distribution.
Yeah, but you have to assume something about the distribution.
Some regularity, just some.
Basically, you have to be able to understand its Fourier transform and analyze it. Because the method, we've always seen that we take the expectation of either the I trace HK.
Yes.
If you are able to understand this, transform it, and figure out how this depends on the Fourier variable K, you can make the next step. If you can't figure out what the Fourier transform is, you're stuck. That's the bottom line.
I mean, supersymmetry is in some sense a big Fourier transformation.
Yeah.
Yes.
That's one can say.
And the easiest Fourier transform is of Gauss.
Of course. Okay, so this is to settle where the problem comes from. So now we fix ourselves on supersymmetry, and we will consider the density of states for a Gaussian unitary ensemble. So just to remember, the model we are looking at is we have a self-adjoint matrix n by n with probability distribution n and we want to study for this model the density of states, actually the average density of states, rho of E, and you have seen that already. This is defined as 1 minus and P imaginary part of sum over J, the average of is this notation clear? Here I mean inverse. Okay, I mean generally mathematicians prefer these notations and the physicists use this notation. Okay, and remember that here input is the average over H, and average over H means integral over dH. And what else? Well, I have just told you that in the case of GUE, you have both statistical independence and invariance under unitary rotations. So in the case of GUE, you can use other techniques. And actually, people study GUE in all possible ways. So we know already that rho of E is equal to the so-called semicircle law plus corrections that go to 0 with n, and this is equal to 1 over pi square root of if E is smaller or equal to 2 and 0, and that's the so-called semicircle law. Yes? Large O. I mean, it says it's not to write, otherwise it would be a 0. Okay? And so just put it over there. And perhaps you know that you can write rho of E in terms of orthogonal polynomials. I don't know, someone I'm sure will know this. And the Hn are Hermite orthogonal polynomials.
This is for finite n.
This is for finite n. And then what people do is to get the expression for rho is they study asymptotics of the orthogonal polynomials, and they get this result. So now we'll try to rederive this expression, but using supersymmetry to show you. Okay, what we write? So, now, as you have already seen, supersymmetry is basically an algebraic tool that allows you to write an expression which is very difficult to compute as a new integral, and which could be still complicated, but the advantage is that in the new integral you can apply saddle analysis. So, in the particular case of GUE, we will see the following. 1 over n, the average of this matrix C, plus an average, sum over j. This is equal, using supersymmetry, to the following integral. I have no room. Times relative. And here, a and b are just real variables, and they are integrated from minus infinity to plus infinity. And E epsilon is an abbreviation for E plus I epsilon. So you see, here you have an integral over h, and in h you have capital N square variables, and n will go to infinity. So it's a huge number of variables. And you end up with an integral over just 2 real variables, which is a big simplification. And moreover, here I have a large factor n. So I can rewrite this in the following way. Oh, the effect of this term is only here, is only this term, little a. If I take it out, the integral is exactly equal to 1, which is, by the way, a very nice identity. Ugh.
It's very much the same thing that David Bridges talked
Exactly.
about.
This is just an effect of supersymmetry, except that to apply supersymmetry, you need to go a step back in the derivation and have here also the Grassmann variables. And then you see it immediately by symmetry. Yeah.
Just small comment that I plan to use different, as you
Notations.
noticed, ratio of determinants.
Yes.
Yeah, it's just obvious because if you put them equal, I mean, 2 equal determinants,
Exactly,
it's just
exactly.
1.
Exactly.
So
Then it's just 1.
At this level, it's even more.
So we have that 1 is equal to the integral over d mu ab. where d mu AB is everything except the term A. Now, notice that this measure is complex because I have E plus I epsilon. But still, it's a measure normalized to 1. It's a very complicated way of writing 1, but it's 1. So, we started from an integral over H with n square variables, and we ended up with an integral over dA dB that is just 2 real variables. And moreover, here we had something we didn't know how to compute, and here we have an expression which is E minus n, a function of A and B. And n is large, so we will be able to justify a saddle point analysis. Now, before showing you how to derive this expression, I will try to convince you that this saddle analysis is actually really powerful. So we'll just go over quickly. Can I write here? Do you see? Okay. So what is I put everything except the observable in the exponential. So we have a function f of AB, which is equal to a square over 2 plus and then there is the last piece. As n is very large, this term is very tiny. And basically, I can neglect it. It will give very tiny corrections to the saddle. So we can actually just look at the first line. Now we compute and the result is that A saddle is E over 2 plus minus I square root of 1 minus E square over 4. And for B, we have I B saddle is E over 2 plus minus I. Well, so you see that this term is already the semicircle law. Now, what is the saddle approximation? Now, I'm lost. Yes. Well, we take the observable and we compute it directly at the saddle. And then we take here the Gaussian approximation of this measure around the saddle. But this measure is normalized to 1. So actually what we will get is that d mu AB A is more or less equal to A computed at the saddle. Now, remember what is the definition of density of states. We have to take the imaginary part of that object. So we have to take the imaginary part of this multiplied by some coefficients. But the imaginary part is proportional to the semicircle law. So we get immediately that this is proportional to of course, we have to check the constants, but it works. But you can see immediately, just by saddle approximation, that you get directly the correct result. And now see, if the energy is in between minus 2 and 2, this object is real. So we really have an imaginary part. If the energy is outside the interval minus 2, 2, this square root is actually imaginary. So the saddle is real, and the imaginary part is 0. So this is fine. I mean, that's exactly what we want to find. Okay, so I hope now you are convinced that it's useful to try to get this representation.
So isn't there an epsilon dependence on AS?
Actually, amazingly, The moment you get here, you can take epsilon to 0. Look at the integral. Yes, sorry, I wanted to say that later, but I can say it here. Here, we have a pole in A. There is a pole in A equal to E plus I epsilon. And so this is a remnant of the fact that we had to put an epsilon to define the inverse of E minus H. So when epsilon goes to 0, this C is divergent. And it's a pole of order n, so it's a huge order. Now, when you want to apply the saddle approximation, the first thing to do is to move your contour in order to pass through the saddle. But this saddle is not real, it's in the complex plane. So you have to translate the contour in the complex plane. And actually, if I look at real part of A, imaginary part of A, here I have E over 2E. Here I have a pole, and there are two saddles, one here and one here. So if I translate the contour in order to pass through this saddle, now I added an imaginary part. And here we get, oh, I don't know where to write. Now it's important that the two imaginary pieces add up. So now if I take epsilon equal to 0, this is still non-zero. Of course, this is true as long as this term does not vanish. So if I approach to the edge of the spectrum, that is E equal 2, E equal minus 2, this term becomes 0, and I have a pole again, which means you have to remain well inside the bulk of the spectrum. Otherwise, you have to do other kind of contour deformations. Okay, it's fine.
Yeah,
So-
I'm still confused. So for the semicircle law, we need the distribution of the trace of h squared, and what else?
This distribution.
Yeah, well,
What do you mean?
there is P of h.
The semicircle law is for the Gaussian unitary ensemble.
You assume the Gaussian
Yes,
unitary ensemble?
yes.
Okay. So
For another probability distribution, you have no reason to think you will get the semicircle law
In general. but,
in general.
If
In
in
some
fact for
cases you do.
independent, you will go with for a huge set of ensemble. There is precise condition.
Yeah.
I think Leonid Pastor, in fact.
Yeah, if the variables are statistically independent,
You will get
Yes,
semicircle, almost. Not always, but almost.
in the invariant case, you can get anything.
so what's the condition for the semicircle?
If you
Then
ask for
The variables
precise,
are- if the probability distribution for the matrix is a product of distributions, one for each variable.
if they're independent and
It's called a
identically
Wigner matrix.
Identically distributed.
Okay.
They could not be
They
mapped,
should
not
be
Gaussian.
Gaussian. They don't have to be Gaussian.
No,
it can be plus minus.
Okay.
In
But there are
fact,
precise
you can take Bernoulli. Each matrix element can be
Zero and
randomly
one.
either +1 or -1. It will be the same circle.
In the limit of a large matrix,
Yeah.
of course.
This is what Wigner first proved. He computed the moment of
Okay.
this, found the Catalan numbers, and realized this is the distribution for this is a semicircle. So this is the so-called Wigner matrix case. Very different are these invariant ensembles. There, as soon as you go away from the Gaussian, you lose the semicircle. You get all kinds of things. You can have gaps. You can have various parts of spectrum and gaps in between. This leads to rich mathematics and lots of efforts on this orthogonal polynomial plus Riemann-Hilbert side, studying all the possibilities that occur and really controlling the asymptotics.
Okay, but then, so again, so what is the class of matrices where you get the semicircle? It's larger.
Okay, so it depends on what you call
The
large.
Wigner
No,
matrices.
it's just matrices with independent entries plus some conditions on them, which I don't like to specify. But more or less, if you are not especially weak, you take independent, identically distributed entries, you will get semicircle. Yes. And yes, and this laws of distribution is not like Cauchy theory, with moments. Not only this, but there is precisely.
Okay, so before going into detail, so what are the main two steps in the supersymmetric approach? The first step is more algebraic. And this is a change of representation. And this means that you rewrite this expression as an integral where you can do saddle analysis. So this is just Now, there is not just one possible representation that works. You have seen in Jan Fyodorov lectures that you could have two possible, actually there are even three possible schemes. You do Haber-Stratonovich, or you change code, you have to do this superbosonization. So the particular representation you choose depends on the problem you're looking at and what is more convenient. But the idea is you have to find a new representation where saddle analysis is possible. And once you are there, now you need analytical tools. To make the saddle analysis rigorous. And this can be pretty hard. And I want to leave that expression and just okay, so for the moment we are here in the first part. We want to change representation. Now, you have already seen that the key idea is to write that matrix element as a Gaussian integral. So now you have already seen this formula that if you have a matrix A, I, n by n, with real part of A, so that is A plus A adjoint over 2 bigger than 0, then the inverse 1 over A matrix element Jk can be written as an integral over product Now, Z are complex variables. I'm still missing something before people start protesting. And here you have already seen this. This is the quadratic form sum over jk, z bar j, hjk, zk. I don't remember what was your convention. Perhaps you were using phi instead of z.
Yeah.
I use yes, phi.
Prefer phi?
Yes, no, I prefer what you are.
Okay. Now, if we take this integral, you will get this expression, but we are missing the normalization factor. If I take away this Gaussian integral gives 1 over determinant of A. So if I want to normalize, I have to multiply here by determinant A divided by 2 pi. Okay? Okay, can we apply this formula over there? Well, it depends. If you can find a matrix A with positive real part, yes. By the way, why do we need a positive real part? Because otherwise this integral is ill-defined. Oops. Oh. Okay, up. So let's see if I take A equal to E minus A plus I epsilon. The real part of this matrix is E minus H. But this has no definite sign, so that's not good. But if I take minus I, A equal to minus I, then the real part of A is epsilon times the identity. And that's certainly positive. So I can apply the formula, but I have to use this matrix. So now we apply it, and we get this is equal to determinant of minus I E epsilon minus H integral over d z bar z. Now, if I have a minus here and a minus I here, we get plus I z bar E epsilon minus H z and z j. Okay, hopefully now I have, no, I was missing a 2 pi. Now I think everything is there. Yes? No? So I just replaced A in the formula by this matrix. Okay, did I gain something? Well, sorry, I'm jumping back and forth. Well, it depends. Suppose you don't have this term. Yes? To epsilon? Oh, sorry. I'm lazy. I don't want to copy each time. So I write E epsilon is equal to E plus I epsilon. So if this term is not there, well then which of course is false. Well, then our matrix element in average is equal, and I will put it like that to say this is for the moment I'm missing some terms, to the average of integral over d and now here I want to write this as sum over j. So here I have sum over j, and this is average over h. Now I can put the average inside, and we get sum but that's exactly the expression you have seen this morning or 2 days ago. And so now you understand why it was so important to study averages of 1 over the determinant, because then you end up with this. Of course, I'm still missing one term, the normalization. We will see that this will create some problems. But now, if I have just this, well, now we can do exactly the average. You have seen this already several times. This integral is just equal to e to the minus 1 over 2n sum over jk z bar j zk times z bar k zj. Okay, so forgetting the normalization factor, we managed to take the average over h. Now the price is that here I still have a Gaussian term, but here I have a quartic term, and I don't know how to compute this integral. I would like to go back to a Gaussian integral. Well, of course I could go back to the initial representation, but that's not very useful. So I want to do something clever and reorganize this so to have a new Gaussian integral. And I write here. Well, I can reorganize this sum in the following way. This is sum over j, z bar j, z j square. Because I just move the zj here, the zk here, there, and this is just a square of a sum. But then this is equal to integral over one real variable so you can rewrite this quartic term as a Gaussian integral, but over just one variable. Here you had n variables. And I'm missing again the normalization factor. The integral here would be square root of 2 pi over n. So it's okay. Now I can take this integral outside and we get that sum over j, the average over h, is more or less equal to integral over dA, and here we have the integral over dz bar dz exponential I z bar z e epsilon, and here we have I a z time. And I'm approximating, this is the sum, approximating this is the notation, because I don't want to copy each time. Well, this object comes from the observable, and I would like to get rid of it. But you see, I can say that this is just the derivative with respect to a of this exponential. And then I do integration by parts, and I move the a on this side. So actually, I can take this away and put here I n times a. So now here I have just a Gaussian integral. And this is actually a product of j of e to the I. E, actually, it's better with a minus, doesn't change anything, but so you have 1 over, there is a minus I, e epsilon minus a to the power n, and there is some 2 pi to the power n. So you see we end up with an integral over a of the exponential minus n a squared. We have e epsilon minus a to the power n, and look, where was it? That's what we should have, this exponential and this term. We have this little a, that was the observable. So we have already a good piece of the formula we want. But we are missing all the b part. Well, that's because we did a big mistake at the beginning. We neglected the normalization factor. And the normalization factor contains the h. So we have to take care of it when we do the average over h. So now we have to go back. Yeah, I still have that. So it was here. And when we want to do the average over h, we still have this object. We can't do the average directly. So we would like to write it again as an exponential. Now, it's impossible to write a determinant to the power 1 as a Gaussian integral. unless you use anti-commuting variables. And that's why you have to introduce these fermionic variables. At least that's one of the reasons.
Are there questions from the audience?
Is this, yes?
I thought you said something about this expectation value there on the right would be 1 over determinant like that in the morning.
You mean
Yeah, that's one.
this? No.
That was a confusing remark.
I'm
You said
sorry,
that
no.
We now see why we have.
Oh, no, sorry.
one
Yeah,
determinant.
sorry. That was what I was trying to say is that Jan Fyodorov, he started talking about averages of 1 over determinant of matrices. And today he started talking about averages of determinants of matrices. And when he talked about averages of 1 over determinants, he ended up studying expressions of this kind. And at the beginning, when he started, he was talking about this, it was not clear why this kind of average would appear. And now you see that, yeah?
So we've done one average, and now we need to do another, but
Exactly.
Is it safe to do them one then the other?
No.
No,
Both
absolutely.
fine.
No, you have to do them at the same time.
Okay.
So this was a mistake.
Okay. So erase them.
Yeah, now you have to erase it. Well, not completely. This is, you still use this formula. We are still here, but now we have to study this average. And in order to do this, we have first to write this determinant as a Gaussian integral. And to do that, we need Grassmann variables. Okay, so, well, we would like to find a formula as similar as possible to this one. So I will introduce, so in the usual formula you have n complex variables. I will introduce 2n anti-commuting variables. But just to, this bar has nothing to do with the complex conjugate. You can just think of it as 2n totally independent variables. It's just, the reason I put Q1, Kn, Q1 bar, Kn bar is just to make the formula as similar as possible to the one with Z1,
My
Zn.
goal was precisely the same, to look them similar.
Okay. And these are anti-commuting variables, so we say that Ki, Kj is minus Kj, Ki. Same for the Ki bar and the mixed terms, which means that Ki square is. In particular, this means that any power series stops at the first order. You just have a function f of Ki1 is actually f of 0 plus UI. So all you need to define to decide what is an integral, because we want to define a Gaussian integral, is define the integral over a constant and the integral for a monomial. And well, you have seen that already. Now the integral over d. Well, I'm used to this convention, but you can put 1 and forget totally the 2 pi factor. Now, with this convention, now you can define a Gaussian integral for fermionic variables. I don't know where to write.
You pull that top 4 down.
I don't want to lose that formula. I don't want to lose that formula.
Far right, or maybe.
Over there, yeah, I can write over there. where I chi bar A chi is the sum over j k chi bar j, and A is any n by n matrix. Now notice that here the formula is true only if A has positive real part. The equivalent in terms of anti-commuting variables, well, has no constraint on A. And you can check it, you can check this formula in the case of just two variables. At least you can convince yourself this is a 1 by 1 matrix. Now, in order to, you have already seen that, to do this integral, first you have to expand this function, and this is equal to 1 minus A. Now, if I take the square of this term, it's 0, and any other power is 0. So I have just to integrate this integral is 0, so I just have to compute this. And now, before doing the integral, I have to bring the variable next to the corresponding d. So, and they are anti-commuting, so this is equal to plus A, the integral over d chi bar 1 chi bar 1. Now finally I have a product of two integrals. They are both 1 over square root of 2 pi, so the result is A over 2 pi. But that's exactly the determinant of a 1 by 1 matrix divided by 2 pi. Okay, so using that formula, finally we can write this determinant as a Gaussian integral. So we end up with and average over h, and we were still missing the observable. So all I did was to add the Gaussian integral over the fermionic variables. And now there is a second term that has h dependence, and that's this quadratic form. Okay, well, now we can do the average over h again exactly. And the result is E so you have almost the same expression as before, but you are adding these two pieces. And they come from the anti-commuting variables. Okay, so we are back to the same problem. We managed to integrate out, this time it's correct, we integrated out the h, but now we have a piece that is Gaussian and a piece that is quartic in the fields. And we would like to go back to a Gaussian integral. So we try to repeat the same trick. We would like to write this as a Gaussian integral over some less variables possible, if possible. So where we develop all the terms. The first term is the product of these two, and we know it already. It was sum over j, z plus j. That's as before. Then we have the product of these two terms. So we have sum over jk and then finally the mixed term. And actually we can rewrite as 2 times sum over jk we would like to rearrange here all the terms in order to have a sum over j of something squared, just as here. Let's see. Here I can move the key j next to key bar. There are 2 jumps, so I have -1 squared. And finally here I have chi bar. If I want to have chi bar chi, I have to change sign. So this is minus so this term is minus so you see that's just like this term but with a minus sign because we have fermions. Here, well, I want to put the term with j next to each other. But one is a z and the other is a chi. And same thing here. So this is sum over k z k chi bar k times I didn't move any chi bar or chi, so I have no additional minus sign. Now you see, here I have something where I managed to sum over the indices. But it's no longer a number. It's an anti-commuting variable. So I can write it as okay, so now we know already that this term was an integral over dA e minus n over 2 a square e minus a. And there was a normalization factor. Now we have the other 2 terms. Well, I know this object is not a real number. It's the product of these 2 strange objects, anti-commuting variables. But still, you can apply the usual formulas and write it as the integral over a real number so you treat it as if it was a real object. And you can show that actually that's correct. But, well. Okay, and the last piece. Well, here I have a quadratic term, but in anti-commuting variables. Well, then I can write it as a Gaussian integral, but I have to use anti-commuting variables. And there is a normalization factor, which is n. You can check this kind of formula for if rho is a complex number. If you take here z bar z, then you can see this is correct, except for the normalization. This normalization factor comes because here we are integrating over Grassmann variables.
And is this really a partial derivative rather than a...
You're right. This is more, you're right. You can always see that it's considered the integral over Grassmann variables as a derivative. So if we put all these together,
just ask, so the alpha and alpha bar are commuting?
No, that's the point. Alpha and alpha bar are anti-commuting variables. This is equal to minus alpha alpha bar. On the other hand, here I have chi bar chi, chi bar chi. I can move the pair back and forth because each time there are two anti-commuting variables. So I move it once, it jumps twice, so there is a minus 1 square. I move it again, but here it's only one.
Formula for alpha is over there.
Yeah.
It's a linear combination of anti-commuting variables with complex coefficients. The result of taking such a linear combination is still a anti-commuting variable.
Oh, each time, I'm sorry. So, now I insert these three expressions and I take out the integral over b, a, and rho bar rho. So we have finally integral of b, a, d, b. And here we have an integral of b of and well, I have to put together all these terms and I can reorganize them in the following way: e to the minus I sum over j you can check it. You can reorganize these three terms as the product of this vector with this matrix with this vector. Yeah, I know, it seems oh, and I forgot there was still the observable. There was a piece which was sum over j, z bar j, z j. Well, again, by integration by parts, we can move it, and it's here. That doesn't change because the a is the same. All right, so this seems like a Gaussian integral, but you see, it's a strange Gaussian because here I have a Gaussian term, but this term is mixing z and chi. So the commuting and anti-commuting variables are mixed up. Actually, in a more compact way, you can say that this is a super vector so all this becomes exponential I sum over j e epsilon.
Yes.
Now, you know how to do Gaussian integral with ordinary vectors. Well, it turns out you can do Gaussian integral with these super vectors. Now, when you do a Gaussian integral, and here you have z bar and z, the result is 1 over the determinant of this. Well, in the generalization, what you get is 1 over the super determinant of this matrix. So what we get is, here. Ooh, I should manage. Of e epsilon minus a. And now notice that we can write this as a product over integrals over each phi j, because a does not depend on j. So it's a product of n integrals, and each of them is 1 over the superdeterminant. And now you have to believe me, one can define the superdeterminant, and what you get is That's the expression of 1 over superdeterminant to the n for that particular matrix. Okay, I don't have time to explain you how to define
I will explain it in
You will
detail,
explain it, good.
yes,
So then I don't have, so that's the result. So now we can put everything together and we will have integral over dA dB and you see that here we have the a squared plus b squared and the e minus ib over e minus a to the n, which is what we wanted in the formula. But we still have this rho. This rho does not appear in the final formula. And we still have this factor. So if you want to end up with a formula with only bosons, with only 2 real variables, we still have to integrate out rho bar. But that's easy because it's just 2 variables. I still have a couple of minutes, yeah. So and here I don't copy each time. Now, we use the fact that rho bar rho square is 0. So, 1 over to the power n is actually equal to 1 plus n. I just take the Taylor expansion, and that's the first term of the Taylor expansion. But this is also equal to exponential n. That's a property of anti-commuting variables. These 2 functions have the same expression. They are actually the same. So this is actually a Gaussian integral. Notice that this parenthesis is exactly what we have in the final formula at the numerator. Now, when I do this integral, I expand this exponential. So it's 1 minus n. The integral over 1 is 0, and this integral gives me 1 over 2 pi. So the result is n. And that was exactly the last piece that was missing in the formula we wanted. Oof. So now I have to finish. Oh. Third time. So here, the piece, the exponential this piece comes from the so-called boson-boson sector. That was just the piece with z bar z square. The piece with the b that's the fermion sector. That was the exponential chi bar chi square. If we didn't have this last term, this integral would be a product of an integral over a times an integral over b. Then it would be much easier to analyze. But there is this last piece, and that comes from the mixing. That's the fermion boson sector. And that's what is mixing A and B. Okay, and I think I don't have time to, perhaps it's better if I stop here. So well, so this is a way to get one representation, and what I'm doing here is to use Haber-Stratonovich. You can do other schemes, and then you will get some expression which is similar, where you can still do Sadel analysis, but you might have different powers, and they are arranged in a different way. But the idea is the same. At the end, you want to do Sadel analysis. Now, I have already shown you that the Sadel, just the Sadel approximation, gives you what you want, the semicircle. Then, of course, you have to work if you want to make this approximation rigorous. And to do that, you will have to control, choose a good deformation. You have to study deformation of your contour in the complex plane, choose a good contour, and prove that the regions far from the saddle are small. And in the case of GUE, it's easy enough. In more complicated models, that can be a big task. And I guess it's a good point to stop, because I'm already. So
Well,
if you to leave some questions.
The word goes over to the audience now. Now is an opportunity to ask. Here's David Bridges.
So, so your finite formula at the beginning had some UNs and some UN plus ones in it, right? I mean,
UN?
UN,
yeah, I
sorry?
didn't quite know what they were because I didn't tune in quickly.
No, there
But you
was
had a finite formula.
Hermite polynomial.
Oh,
Let me
the
pull it.
HN, yeah.
HN.
That was
Right.
Right.
and actually, by the way, these, you can rewrite it as these products of Hermite polynomials, just using the integral representation of Hermite polynomials.
Not quite. I would say
No?
not quite. You can, of course, rewrite density, but here this is not density. This is still contains epsilon. And
Yes.
basically, it will involve
Oh.
Hermite polynomials and Cauchy transforms of, or so some integral
Sorry,
transforms.
you're right.
Yeah.
In the limit epsilon going to 0,
Yes,
this
of
becomes, you're right. But you have to do the integral representation and then take the limit epsilon going to 0, you get a residual,
Yes.
and then you have the
Then
Hermite
you have
polynomials,
this,
you're right.
But this, in fact, brings us to an interesting question. You may ask, what in this language is supersymmetry, which amounts to the fact that if you just omit one factor in an integrand, you'll get 1. And I just, for curiosity, analyzed this fact using this integral representation. And this is nothing else as Wronskian identity for Hermite polynomials and second solution of the same differential equation, which is Cauchy transform of Hermite polynomial, which is not polynomial but related to it. And this is just Wronskian identity because they satisfy the same differential equation and gives 1. And this is generally valid in more general context if you use orthogonal polynomials. These identities are just Wronskian identities disguised in this form.
But can you see the supersymmetry back in when you still have the row?
You mean directly? No, in the row, yes.
Yes,
You see, in the row,
in initial it's true, but just on this
in the
language-
row,
No,
I didn't
initially,
write it.
yes, but I
Yes.
mean you got down to an A, B, and a row integral, right?
You mean when I
Still
integrate
is,
it,
but it's
as
not-
long as I have the row.
This guy is already
Here it's very well disguised, yeah.
Yes, but even on this level, it's just some integral identity. What is this identity? It turns out that this is disguised version of Wronskian.
But David, I guess, is asking, where is the Q?
Yes.
Is there a Q?
Is there a Q in the
There is a
AB
Q.
row?
Yes, and
yes,
it's
yes.
very similar to yours.
Yes.
You can't really write it in terms of the exterior derivative because that depended on the
Sure.
fact that you were working with differential forms.
Right.
That you had phi's, d phi's, and d converts one to the other. So, as I mentioned, the d is converting bosons into fermions. So it's raising the degree in the Grassmann algebra, and it's lowering the degree in the polynomials of the complex variables. Albert algebra of polynomials in the complex variables. The Q is, so you don't have P here, so the Q will look a little different, but it is
It's still
morally
going to
it's
be
the same as your
so
Q.
an annihilation.
It
and
has these
creation,
properties that Q square is a Lie algebra element. If it's not 0, sometimes
Yes.
it may be just 0 because the Lie algebra is trivial. And you can use exactly the calculation that you showed, is deformation. That you multiply by some nice localization function with a parameter t. For t equals 0, you have the original integral, and then for t to infinity, it localizes at a fixed point of the vector field that goes in the definition of Q. So we can do exactly these things.
Yes.
Of course, not for her integral,
No.
but for the integral, dropping the a.
Yeah. So we have some homework, we have to do that.
Okay.
Yeah, I've got also a question.
Yes.
You said from the beginning that, well, basically to perform all this stuff, there were two steps. The first was the algebraic one, I suppose this was.
This was the
also what
algebraic
you-
step, yeah.
And the second was the analytical one. And
Yeah.
well, what makes this so difficult then?
Oh,
This is-
well,
okay.
okay, well, in this case it's not very difficult, but still, look, just to have an idea. Here, I have a pole of order n in A. So I have a pole here, and I have two saddles here and there. Now, I have to choose a good contour deformation. And typically, the idea is to say, well, I don't want to cross a singularity, because otherwise I have to compute a residual, and that will be a residual of order n. That's not very nice. And second, I would like that once I am on the new contour, now in this case it's just a translation, the function in absolute value should take maximum value at the saddle. As long as you are well inside the bulk, it's easy. You just do a translation. And then you have to actually study, cut a small region around the saddle, prove that here the dominant contribution is A at the saddle plus something small, and then show that in the other regions you have some exponentially small term. Here it's all right. First problem, what happens when you get near to the edge of the spectrum? Well, then this imaginary part goes to 0. And then actually, if you just keep the translation, you will get closer and closer to the real axis. And be careful, now I'm taking epsilon equals 0, because at the beginning I said, okay, now I have an imaginary part, I can take epsilon equals 0, there is a pole here. And suddenly I have a divergence. So the saddle approximation is just wrong. I'm choosing the wrong contour. And then you will have to do strange stuff, for instance, turning the contour. And you might have to turn the contour according to the region. So it can become.
This even should produce then different asymptotics, because closer
Exactly.
to
And then you get
some
near to
airy
the edge, you
function.
get a different asymptotic.
Yes,
Yeah.
so there's an area function.
Yes,
Exactly,
there is that,
exactly. That's the first problem. Second problem, this is GUE, but in real models, you will never have a formula that easy. Now, the nearest thing I can show you is when you have a band matrix. I don't have time to explain you what a band matrix is, but the spectrum of a band matrix is very similar to the spectrum of random Schrödinger. And in that case, this formula becomes a product of J from 1 to n. Here, instead of having just this, so I have, instead of having just one A and one B, I have one A for each lattice point and one B for each lattice point. So now I have a huge number of variables. And here I have a quadratic form, A, J minus 1A plus B, J minus 1B. There is some quadratic form. Here I have a determinant, and here I have a product of a J of this thing. Now, you can still repeat the saddle analysis, but now you have to do it in each variable J. And you have the additional problem that you want to control your expression when n goes to infinity. So the number of your variables goes to infinity. And
Not
it
n.
becomes quite,
Your n is fixed, you're right.
yeah, but then it's the volume, then you want to take the infinite volume limit. What is fixed is then the bandwidth, but I should explain. So that's an additional problem. It's actually what is very hard then is to control this infinite volume limit. And then you have to start cutting your volume in small pieces, and when you have a few number of variables, then you can do saddle analysis and justify it. But then you have to control the volume going to infinity. And that's not an easy task. And if you have a third problem, that's the last one, for the density of states, generally the saddle is a point, or a few isolated points. Then all you have to control are fluctuations around these points. But in really interesting problems, when you want to study statistics of two-point correlation functions for the eigenvalues or localization properties of the eigenvectors, well then typically the saddle is a manifold.
As I showed on one example.
And you will see, then you have a full manifold, then this large n, the large factor, allows you to control fluctuations around the manifold. But on the manifold, you have no mass. You cannot take epsilon to 0 in that case. And it can be very hard to control the integral around that. So that's why the analytical part is actually tough.
Yeah, thank you.
Sign up.
Sorry?
Still not resolved.
Other questions?
Very good. It seems that you're satisfied. So let's have tea and then come back at 4 for the poster session.